All right, the final lesson of this module, we're going to talk about SDN again, but specifically how that applies to our data center environment. So we're going to look at this application-centric infrastructure, how we can, well, what the different components are, right? And this is significantly different than the enterprise or the EM version that we saw previously. So we'll look at this DCI or ACI architecture for the data center. We'll look at the different fabric components, the role of what we call network virtualization overlay technology in this SDN solution and the Cisco ACI solution, and basically just look at the building blocks and the requirements for designing profiles and whatnot in Cisco ACI. And then look at the APIC network application profiles and designing APIC network application profiles for our existing platforms. Okay, that's what we're going to talk about in this particular lesson. What we're seeing in this diagram here is an illustration of what we call the Cisco One architecture, Cisco Open Network Environment Architecture. Okay. We know that that is going to use the Cisco Application Policy Infrastructure Controller, APIC, for the data center to simplify and streamline the overall management of the hosted applications that we have in our data center. Okay. The APIC controller provides that, and we saw this when we talked about this in the EM environment as well, that open kind of programmable approach to networking through open APIs, policy-based management, security management. So it's going to automate what typically we would have had to do manually over the scope of our network. So we had APIC EM, and APIC EM architecture was specifically related to the WAN and the access layer, like IWAN and our network access. But now we're going to talk about APIC-DC and how the open flow architecture, 1PK, etc., allows that southbound API to control our data center configuration. All right, and the northbound AP is, of course, the Cisco Open Network Environment. And overall, this comprises that Cisco One platform. So I don't know how much detail we'll get into it, but hopefully we'll be able to describe at least some of this architecture. Okay, so the ACI the ACI Fabric, another politician resigning. Yeah. Because of lewd photos, yeah. So the Cisco Application-Centric Infrastructure, I guess from a Cisco speak standpoint, it's scalable. It provides multi-path functions. It's got a high-performance architecture, a little bit different than some of the architectures that we've seen in the past, right? We've been talking about traditional data center architectures up to this point, but now we get into this leaf and spine architecture, right? And the leaf and spine architecture provides a VXLAN overlay for the tenant space that we're going to have in our data center architecture. All right, that's what we're going to see in use by business applications, customers, etc. The ACI Fabric also implements a concept called infrastructure space. I didn't necessarily see that term described on the exam, but it is something that Cisco likes to use to describe the overall ACI Fabric. The idea is that we're isolating the fabric. So when we're doing things like topology discovery, fabric management, infrastructure addressing, and so on, that's going to happen in that infrastructure space. ACI is essentially a very comprehensive software-defined networking architecture. All right? We use policy-based automation solutions so that we can apply policies to our business-relevant applications. We have business-relevant application policy languages, open languages that support scalability through distribution systems. It gives us essentially a much more broad sense of network visibility, right? Because we're not looking at individual components in the network, we're looking at the whole architecture as a whole. All of this is realized through this architecture, right? We have physical, we have virtual environments, we have policy models for our networks that are pre-configured, we have policy models for our servers that are pre-configured, storage components, services components, security components, and so on. So the diagram itself, what you're seeing here, gives us a comparison to a traditional tiered application architecture, which then gets deployed in our ACI Fabric. And we define, and you can see that listed here, we define the objects and the communication requirements that actually get sent back and forth between these components. So we see our traditional tier design, we have our outside tenant VRF with QoS and a filter, we have our web component, our application component, our database component, and so on. So we're going to look at the ACI Fabric, this spine and leaf or leaf and spine topology, and see how that changes the communication model that we would typically see in a data center. So we'll take a look at that here on this slide. Now, Gates, you mentioned this before, this spine and leaf or leaf and spine topology. Let's talk a little bit about what this represents, all right? There are essentially two layers that exist, the spine layer and the leaf layer, or the leaves that exist. And keep in mind, this is with the Nexus line of products, right? The Nexus 9500s or the Nexus 9300 series products. The spine, as the name kind of implies, is the top level high performance switch fabric that interconnects all of the different leaf devices. It's the backbone, right? It's the backbone of our ACI Fabric. And we can see that, well, that's visually represented right here as the spine. The leaves themselves are the bottom level switches that connect all the servers and all the other parts of the network to our ACI Fabric. So our server infrastructure is kind of listed separately. It connects to all these different leaf nodes, and then the leaf nodes connect to the different spine nodes through the ACI Fabric. Okay. The entire environment, including the actual servers themselves, are controlled by the APIC controller. The Nexus switches have to run in what we call ACI Fabric mode. That is a different way that these devices operate, right? So that they can participate in the ACI Fabric. They can run standard NXOS, and they can run in standard NXOS mode, but then they're regarded as kind of an individual device. They're not part of this ACI Fabric. So you can configure these 9500s or 9300s in NXOS mode, or you can configure them in ACI Fabric mode. If I decide to use NXOS mode, though, they're not part of the ACI Fabric in any way. They're individual devices. All right? The controller itself, the APIC, is a physical appliance. It gets connected to the leaf layer, and it's responsible for doing all the initial bootstrapping of the fabric, and that's why it has to be a physical device, because the virtual device relies on what? Virtual devices rely on the fabric. Well, it's a chicken or the egg kind of thing, or the cart or the horse kind of thing, right? I can't have virtual devices connected to the fabric if the fabric's not available, if I haven't constructed the fabric. So that controller is a physical appliance. It is still connected to the leaf layer, but it's a physical appliance, all right? The APIC is distributed. It's logically centralized. It provides things like DHCP, bootstrap configurations, image management, and so on for the fabric, which allows for automated startups and upgrades. But even though it's physically distributed, it's still logically a centralized controller. The Nexus ACI Fabric software is actually bundled as an ISO image, which is then installed on the appliance server through the actual serial console. So the ACI software ISO that you get from Cisco contains the APIC image, it contains the firmware images for the specific leaf nodes, and the firmware images for the spine nodes, and a default fabric infrastructure policy with all of the predefined protocols and the protocols that are required for the operation of the ACI Fabric. It's almost like a plug-and-play deployment, right? It's a little bit more involved than that, but it's a very simple, relatively speaking, a simple deployment option. So if I look at this diagram here, it identifies a set of devices that are used to build this ACI Fabric. There are some minimum sizing requirements that Cisco recommends, and this would be something that might be on the test, but I don't know if you guys can let me know if you saw something like this on there. But the minimum size, there should be 3 or more controllers. Huh? No? Okay. Yeah, so you might see it on a different test. It wasn't on your test, but yeah. So 3 or more APIC controllers. Those will be dual connected to different leaf switches so that we can have that resilience and that redundancy. Remember, the fabric is manageable even with just one controller. And it can actually operate even if there's no controller. You can't change the configuration and you can't modify the overall design without the controller, but it will function, the fabric will function without an active controller. The next recommendation or minimum sizing requirement would be at least 2 spine devices. Again, we can operate with 1 spine device, but we're not going to get load balancing, we're not going to get resilience in the design, so the spines need to be added in a redundant fashion, and at a minimum we should have at least 2 spine devices. And then at least 2 leaf devices, again, to connect our servers and our devices to this spine and leaf topology, we want to have 2 leaf devices for redundancy, all right? And then every leaf node, regardless of however many leaf nodes you have, every single leaf node should be connected to every single spine node. Not just 2, because that would be kind of our traditional 3-layer architecture that we saw in a network-centric design, right? Where we have an access layer, distribution layer, and a core layer. But in this case, with the spine and leaf, we don't really have that. All of those leaf nodes should be connected to every single spine node that's introduced into the topology. All right? The data center can be integrated into an existing data center, or we can migrate to this new fabric using lots and lots of different options, right? We can migrate hosts to the new fabric, so kind of have a greenfield installation, have this ACI Fabric built and constructed separately from our traditional data center design, and then start migrating users or hosts over to that new fabric. We can move fabric extenders over to the ACI Fabric. So moving multiple devices at the same time. Remember, we're building this ACI Fabric with Nexus switches, the 9500 series, the 9300 series switches. So we're able to incorporate those fabric extenders into that ACI Fabric. We can migrate the aggregation of the Nexus 5000 series switches and whatever dependent fexes that they have to this ACI Fabric as well. So even though the control function, the spine function, is still a 9500 or a 9300, we can aggregate the 5000 series switches over to the ACI Fabric. And then we can create just an interconnection of the existing data center to the new ACI Fabric and have that cross-connect communication. Whichever option you choose, whichever design model you choose, you need to make sure that you have layer 2 connectivity between the host segment and the leaf so that we can benefit from that APIC managed services and those end-to-end services that the APIC environment is going to provide us, okay? This diagram gives you those options, right? We'll just migrate the FEXs over to the Fabric, migrate our 5000s and our FEXs over to the Fabric, or just connect our existing data center to the Fabric, all right? We didn't see really option 4. It wasn't listed on here. Option 4 would just be to connect hosts to the Fabric. Out of all these options, probably the one that you would start with would be this one. If you have an existing data center architecture, because you want to have connectivity from your existing data center, and then you can start to migrate over to one of these options or one of these options later on. All right? It depends. It depends on what your connectivity requirements are and what your goals are with this migration. Now, we have talked in length, actually, about VXLAN and about the overlays and what overlays are used for, right? In the ACI network, though, what we didn't identify yet is that we actually use an overlay based on the VXLAN technology. And that is done to virtualize the physical infrastructure that's used in this ACI Fabric. It's going to require a data path at the edge of the network so that we can map from the tenant endpoint addresses in the packet, which is the identifier of that packet, to the location of the endpoints, which is the locator. So there's the two terms that we didn't see previously. We were talking about our overlay networks, right? The identifier is the tenant endpoint address, and the locator is the location of the endpoint the physical location of the endpoint. Remember, VXLAN virtualizes that by creating this layer 2 domain over a layer 3 routed domain, okay? That mapping occurs in the TEP. We talked about that before, but since the overlay networks are virtual, they are very, very suitable for automation, and that's where we see the APIC-DC or the APIC environment come into play here, because they're dynamically created, because they're virtual, they can be controlled through software and through this software automation. All right. Now VXLAN, you know, we talked about the name, right? It's basically designed to provide Ethernet layer 2 network services, much like a VLAN does, but with much more extensibility. And that's actually what the X stands for in VXLAN. All right. What are some of the benefits of VXLAN compared to a VLAN? Any ideas? Well, probably the biggest difference, right, is the ability to extend the VLAN over an underlying network infrastructure. We can't do that with a real VLAN. In order to extend a VLAN, we have to use trunks, we have to use layer 2 interfaces to extend a VLAN. But with a VXLAN, we can extend our layer 2 segments over those underlying shared network infrastructures so that the tenant workload can be placed across different physical boundaries, right? Logical boundaries as well. Also, well, because of that, we get a lot more scalability. Remember we talked about with a VLAN design, we have a limitation, don't we? We can only do 4,000, mathematically speaking, 4,096 VLANs, because the VLAN ID field in our layer 2 header is only 12 bits. So that limits the scalability of only 4,094 VLANs. Zero is not used, and 1 is default, right? Because VXLAN uses a 24-bit segment ID as opposed to a 12-bit VLAN ID. By the way, that segment ID is called the VNI. That gives us up to 16 million different VXLAN segments. It's obviously more than 16 million, but we kind of round down, right? Because we're doing binary math. 2 to the power of 24 is just over 16 million, okay? So we have a lot more scalability, a lot more growth potential in that regard. Because we can also use the underlying infrastructure, we have the same, well, I wouldn't say the same, but we have better network path selection. If I'm extending a VLAN, I have to use legacy protocols to protect that VLAN against issues, right? Spanning tree, for example, has to be used for loop prevention, all right? And that means that in the end, half of the links end up getting disabled because of the spanning tree algorithm. In contrast, VXLAN packets get transferred through the underlying network based on layer 3 header information. So now we don't have to worry about spanning tree. We don't have to worry about links being disabled or enabled and so on. We take complete advantage of that layer 3 routing topology, all right? So we can do link aggregation, we can do first hop redundancy, we can do ECMP routing. There's a whole bunch of things that we can take advantage of that we would never be able to do within a regular VLAN. So good stuff, all right? Now we talked about VXLAN, but there was another protocol that also provided the same or similar function, which was NVGRE, right? That's the network virtualization using the generic route encapsulation. Same thing, it allows the creation of these layer 2 topologies on top of a layer 3 domain. In the case of NVGRE, though, how does it work? How is it different from a VXLAN? Do you guys know? It does tunneling, yeah. It tunnels the Ethernet frames inside of an IP packet, basically, right? It's very similar to VXLAN. It even has a 24-bit segment ID, just like VXLAN does. In this case, we call it a VSID, but so that's also going to provide 16 million virtual segments and so on. Very, very similar protocols, not a whole lot of difference. But VXLAN is really probably the primary protocol that you're going to see in the case. Have you guys ever had a chance to actually implement that technology before? I was waiting for Gabe to give me a story.
What does it stand for? What does it stand for? Yeah. No, I was just watching other people doing it.
Yeah. Right. What we're seeing on this diagram here is our traditional 3-tiered application, and then how that can be described as part of the APIC environment, right? The application network profile contains our application policies. The policy consists of these things called EPGs. An EPG is an endpoint group, and so the policies are going to contain those EPGs, and then excuse me, and the EPGs themselves. Well, we'll talk a little bit more about EPGs as we kind of move into the details here. And there were a lot of questions on the test about that concept, at least the ACI-related questions anyway. But a policy consists of a number of EPGs. Those are typically one or more servers that are in a common subnet, so they're going to be providing common services on the network. And then we have policy contracts that define the communication requirements between the EPGs themselves. Almost like what's allowed, what's not allowed, what are we allowed to communicate between these different these different groups, right? So an EPG is just a collection of endpoints that provide a similar function. Maybe it's they represent an application, a set of services, or whatever that are going to run on the network. And essentially what this does is this allows us to provide a logical grouping for objects that require similar policies, policies that are driven and defined by the controller and pushed down by the controller, all right? An example would be a group of components that maybe make up an application web tier. What goes in an application web tier? Public-facing servers, right? Internet servers, web servers, and so on. The endpoints themselves get defined by using their NICs, the VNIC, IP address, DNS name, and various other methods that allow us to identify those application components. The concept of an EPG is that it's supposed to provide flexibility, all right? It's supposed to allow, well, the creation of these EPGs is supposed to allow their use to be customized to a deployment model with a particular given customer, whatever that customer might choose to do for that particular group. And then we use those EPGs to define where policies get applied. So within the ACI Fabric, the policies are always, and we can see that listed here, the policies are always defined between the EPGs. By defining those policies, we're defining how EPGs communicate with one another. This is, well, if you go and read Cisco documentation, they'll note that this is supposed to be extensible for the future, right? What are you doing?
What do you mean? That's Patrick.
Oh, okay.
You pretty much said the stuff with the drag and drop and matches so far.
Oh, okay. That's fine. So the implementation of the EPGs within the fabric provides quite a few different benefits, right? EPGs act as a single policy enforcement point for groups or contained objects. It simplifies the configuration of those policies. It makes sure that the policies are consistent. If additional policies need to be applied based on not a subset, but the EPG itself, we can do that also. Because we're applying the policies based on this relationship within the fabric, that means that the IP addressing changes to the endpoints themselves don't actually change the policy because we're not applying the policies directly to the endpoints. You know, when we look at traditional network design and you look at traditional networks, it doesn't work that way, right? In traditional networks, we usually apply policies directly to an endpoint. Additionally, moving an endpoint to another EPG would basically mean that the policy that's tied to that EPG would be applied to that particular endpoint. Maybe it's a leaf switch to the endpoint to which the endpoint is connected, and by attaching that endpoint to that leaf switch, that defines the new behavior for that endpoint based on the new EPG that it's assigned to. It's a very interesting concept. I mean, it's not a new concept. We've seen group policies and group policy implementation quite a bit in a lot of different network implementations, right? Particularly with Microsoft and other types of systems like that. When I'm designing EPGs, the ACI EPG provides a new model for mapping applications to the network. Instead of using standard forwarding constructs like addressing or VLANs to apply our connectivity and policies, EPGs use a grouping of application endpoints. We talked about that on the previous slide, right? So the EPG itself acts as kind of a container for the collection of those applications or application components or the application endpoints. And it tiers, and the application tiers, right? Anything that has to do with the particular application. The benefit of this is that it allows the separation of our network policy, our security, our forwarding, and it separates all that from the addressing component and instead applies it to the logical application boundary as opposed to a specific device boundary. Okay? So what are endpoint groups comprised of? Well, they're a collection of servers, okay? So that's number one. Those are the devices that are going into the endpoint groups. There's a contract. Contracts are provided and consumed. That's directly related to a test question. A contract basically defines the layer 4 protocols, the ports that are allowed, et cetera, et cetera. And there's an implicit deny with the contracts themselves, much like you would see with most security architectures. We have something called a bridge domain, which is just our distributed virtual switch. And we have the network, which is the layer 3 network with our gateway functionality for the attached bridge domains to apply layer 3 routing or layer 3 processing between the different bridge domains. We'll get into this in a little bit more detail as we move through the rest of this chapter. Right? An application network profile, ANP, application network profile. It's not listed on the slide here, but it's a very important concept, particularly when we're talking about the EPG components, the contracts, the bridge domains, and the network function. This application network profile is a collection of EPGs, the connections that are used by those EPGs, and the policies that define those particular connections. So it represents the logical structure, if you will, of the application and all of the interdependencies that that application has within the ACI Fabric. They're designed in a kind of a logical way that matches the way that the applications are designed and actually deployed. I'm probably not describing it very well, but you kind of think about it as a profile that's defined based on the overall design of the application itself that's part of the EPG. It's going to include configuration and enforcements of policies and connectivity that gets handled by the system. And instead of the administrator having to manually configure that, this application network profile handles that configuration. The diagram that you're looking at shows kind of an example of an application profile. The contracts define our inbound and outbound permit and deny policies, our QoS rules, redirect rules, etc. And so we see a contract provided for the EPG, and then contracts consumed within the EPG, and then we have our bridge domain and our network, our layer 3 entity. So what does a contract specifically do? It gives us the ability to apply simple and complex definitions of the way that the EPG communicates with other EPGs. Think of it as, I don't know if you guys have ever had a chance to work with zone-based firewalls, but we create these groupings of interfaces, and then we create these zone pairs, which is basically groupings of interfaces that are paired together. And then we have a policy, a zone-based, a zone pair policy that we apply that allows traffic to flow from one zone to the other zone. Well, it's a very similar concept here. The only difference here is it's called a contract, and it defines how the EPGs communicate with each other. And that contract can be written or defined based on whatever the requirements of your environment are. All right? Now, contracts are actually enforced between EPGs, but even though they fall kind of between the EPGs, they're actually connected to the EPG using provider/consumer relationships. Hopefully we'll see a little bit more about that later on. But basically what it means is that one EPG provides the contract and then another EPG consumes the contract. We don't see it depicted here, but you know, I would see an EPG here and I would see an EPG here, and we'd have the flow of information that way. Okay? All right. Now, there are 3 different types of design tasks when it comes to designing our applications. And we can see them listed here: a greenfield, designing based on known existing applications, or designing based on unknown applications. Greenfield basically means that we don't have to depend on any existing environment. We are simply designing for a brand new environment. And that's by definition what a greenfield environment is. The designing for known existing applications, of course, means that you have to understand what the existing parameters are, and we have to then map those existing parameters into our ACI profile parameters to make sure that it corresponds to what we're trying to accomplish with the APIC policy creation. Designing for unknown existing applications is really the biggest challenge. Maybe we don't have all of the required data, or the data is unreliable, which kind of makes mapping, well, I guess it kind of makes it impossible because we simply don't have the appropriate information that we need in order to facilitate the mapping. Overall, the simplicity of this application profile modeling is that it only requires a small set of data that describes either existing applications or new applications. And I'm kind of looking at this diagram while I'm trying to identify what it is I want to say. But this is obviously related to a greenfield environment, which would apply to new applications, or existing applications, which would apply to known applications. In an optimized design, we can model that design and implement that design using our APIC application network profiles based on what we created. All right. So the first step would be to design services for ACI, our application optimization services, and then the second would be to model the services within APIC to apply the ACI approach to those particular applications. But what do we do if it's an unknown application? How do we handle unknown applications? In order for us to design application profiles in APIC, we would have to know the application architecture. We would have to know how it's addressed, how it's routed, what is its security functionality, right? In other words, its footprint on the network, what kind of ports does it use, what are the protocols that it uses and so on. So we'd have to know that information in order to really create a profile. Otherwise, if we don't have that information, then it becomes nearly impossible, right? If we have a lack of documentation, regarding our existing set of applications, which could be lots and lots of applications, it prevents us from really designing an equivalent application using APIC. Okay, it's not that there's a generic bucket that we can just put these applications in and have them function the way we want them to function. It doesn't work that way. We have to have some knowledge of the applications that we're trying to build and apply. So we have to analyze those existing applications. We'll have to go through a thorough analysis of our existing environment before we can even think about doing any application design steps to provide a set of information describing the migrated applications to the APIC Fabric or the ACI Fabric. Now we can use protocol inspection, we can use net flow, connectivity rules, devices that are processing data through for that application. We'd have to basically become detectives and go through the whole process of identifying those application parameters. Because remember, those 3 bullet points that I talked about before, we need to know. I mean, it's the application profile that we're trying to build. Otherwise, we can't. We won't be able to apply what we need to apply to the design. All right. So in this lesson, I guess we talked about various aspects of APIC and SDM, APIC-DC, and what we use, the tools that we use to do this. For example, the APIC controller for our network-wide management, our API open interfaces, REST with XML or JSON or partner applications. We didn't really get into REST or JSON in this section, but that's kind of assumed when you're talking about the ACI Fabric. The abstraction of devices and network topologies using EPG contracts, network application automation, automation of the physical infrastructure, and then mobility resources. This is an interesting summary page because I don't remember talking about any of this stuff in this chapter. But anyway, that's it for that lesson. And that's actually technically it for that module. We are finished with that module. And so what we're going to do is we'll move on to the next module.